Okay, I'm in Atlanta in my hotel room. I'm waiting. I missed the first session of the conference because I got here a little late, but that's okay. I'm gonna record this video for you guys and then I'll go to my first session. So, um, we are finishing up lesson 5 here. It's just a few slides, but they're all very computational problems. I'm just gonna kind of walk you through them. I'm gonna pause every so often, try and think it through, dealing with again friction. So this question number 2 was referring to a ramp that is at 30 degrees using a 2.5 kilogram book. What we're going to do though is we're going to push up the ramp with an initial velocity of 4.2 meters per second. So we're going to find out later that there's a way to figure this out, but I pushed with such a force that I caused this initial velocity. And then we still have the same coefficient of friction of 0.35. How far up the ramp does the book go before coming to a stop? So please take a second and draw your FBD. Okay, here's my FBD. I'm going to try and draw this as good as possible here with my janky. Here's my X, here's my Y. Now, careful with this. Let's think about the direction of travel. The travel is up the ramp. So hopefully you drew this correctly. Here's FG. Yeah, here is FGX. You're gonna have to excuse my really terrible handwriting right now. I lost my stylus for this. And so it's just my finger on my touchscreen computer, and there's FGY. Now, if travel is up the ramp, which way should you have drawn friction? Friction is gonna go down the ramp actually this time. If I'm going up the ramp, friction fights against the direction of motion. Now, I've pushed and let go. Yeah, so you should not have put any push up the ramp as a force for that velocity. I've already done the push and then I let go, so that the second I let go, that is the initial velocity. And hopefully you can understand that obviously as it goes up the ramp, it's going to slow down. And not only that, it's going to slow down because of gravity, but also because of the friction. So I want you to first off read the question. There's a hint here that we're going to have to do something besides just do our F nets. If it says how far up the ramp does the book go before coming to a stop, what are we looking for? What variable, what quantity? How far is a distance? It's a position. We want to know X final. This is your key that you're going to have to do a kinematic equation. But we know that in order to do a kinematic equation, if we were to lay out my variables here, 1, 2, 3, 4, 5, I have X initial, X final, A, T, velocity initial, velocity final. Okay, we have to know one of these variables because all 3 of our kinematic equations use this variable. This was a Jeopardy question. What do I have to know before I can do any of those big 3 kinematic equations? We have to know A. So when I'm dealing with forces, I can find A in F net, right? Because F net equals MA. So we're still going to do that. We're still going to just do F net equals MA. Get A and then go from there. Actually, I lied. Before we get A, go ahead and fill out your variables of what we know so far. We do know a couple things. Okay, so X initial is going to be 0. X final is the question mark, right? We're going to call wherever it's at currently when I let it go. I push it, but right there, we're going to call that 0. And then wherever it ends, that we're going to call that X final. I don't know A. I need to find that. Do we know time? This time? Well, no, we don't. Don't know time. Hey, there's the key there. We do know the initial velocity, 4.2. Now, we do know something else as well. What else do we know here? It's not time, so what else do we know? We know the final velocity is going to be 0. It says before coming to a stop. We want our final velocity to be 0. So again, hopefully you can tell we're going to use timeless. We don't know time, but we have to find A using our F net. Now, sorry, I just realized that I left off the normal force here. There we go. So here is how we find acceleration. We have 2 versions of F net, right? We know F net equals ma by Newton's second law, but we know the definition of F net is the sum of all forces parallel to the direction of travel. So look at our travel. Our travel is in the x direction up the ramp. What are the forces that are in that direction of travel? There are two. Well, I've got, let's get a highlighter going here. I've got FGX and I've got force friction. Those are both x directions because again my x direction is tilted, right? So my F net is going to be, now also be careful here, what do we notice about the force of friction and FGX? Are they pointing in opposite directions or the same directions? Same direction. So we are going to add them together. For Pete's sake, there's our purple. There we go. Force friction plus FGX. They are both pulling, there we go. They are both pulling that object down the ramp. So we know that I am going to set these two things equal to each other. This is going to keep happening, guys, with anything we do in this class. You're going to keep expanding. So let's go ahead and expand this once more. I know the formula for the force of friction. Please look in your notes. What's the formula for the force of friction? It's kinetic friction, but what is it? Well, it is the coefficient of friction times the normal force plus, we have FGX. We can expand this one more time because we know what the normal force is, or we can find the normal force because the normal force is all y direction components. It's FGY plus or minus if there's other y direction components acting. So look at our FBD. We only have one y direction component. What is it? It's only FGY. So the normal force in this case is FGY. Again, be careful. If there was an angled force, or if I was pushing down on the object, I'm going to increase the normal force. So it wouldn't just be FGY, it would be FGY plus my increase downwards, yeah? So here's what I've got. Now I can also go ahead and take this around here because these both equal F net, right? And so they can equal each other. So I want you guys to go from here. I've given you enough information. Go ahead. We need FGY and FGX. You got to do some trig. Yeah. We're going to solve for A. So let's go ahead and solve for A. Well, okay. I've got my mass is 2.5. I've got A is what I'm trying to solve for, right? A is not our end goal. But I need it to be able to find my end goal. We really always like to start with our end goal. Again, that's over here. Whoa, God, that's over here. This is our end goal. Always keep that in mind, but we need A first. Okay, mu is 0.35. And I'm going to go over here actually and get my FGX and FGY. So here is FG. This is 30. Here is FGX, FGY. So for FG, I should have 25. Yeah, it's the same 25 here. Now, you guys already have FGX and FGY. I forgot from a different problem. So I can look those up real quick here. It's my FGX, my FGY, because it's the same as this guy, right? Yeah. Okay, so FGX 12.5 and then 21.65. Make sure I got that right. FGX 12.5. Okay, it's come back up here actually. So 0.35. Oops. FGY was the 21.65. Carefully to get these jumbled. Plus 12.5. Yeah. Okay. And then we're solving for A here. Once you've got that, this is just basic arithmetic. So I'll try and do this kind of quickly here. I've got 2.5A. I'm going to pull up Desmos here. What was it? 0.35, 21.65. 0.35 times 21.65 plus 12.5. 20 point, I'm going to go ahead and just round this off. I'm terrible about that, but whatever. 20.08, I'll call this. And we just need to divide by 2.5. A equals 8.32, okay. Meters per second squared. Now, we do need to realize something about this. I prefer to do it this way just so I don't get jumbled up in the mix of things. I need to think at the end if my acceleration is going to be negative or positive. Because both of those forces were in the same direction. Friction was pulling down the ramp, gravity was pulling down the ramp. But our travel is up the ramp. So are we slowing down or are we speeding up? Well, we're going to be slowing down, right? We're going up the ramp and going to come to a stop. So when I write this up here, this is actually going to be negative acceleration, 8.32, because I need to come to a stop. So it is up to you from here. You should know how to do it. This is the timeless equation. I shouldn't have to ask you that. You should know if t is blank, timeless. All you got to do is plug everything from here, get the x final, and that's that. So I'll give you a second to do that, and then we'll move on to the next question. Enjoy people around you. I just been trying to save time here. I need to go to my first session in just a bit. So you should be able to plug into the timeless formula and find x final. Okay, let's go ahead and look at the next one. Move me over here. Okay, so example 3, it says you place a block of plastic that weighs 33 newtons. Hey, weighs 33 newtons. This is a certain force. What is weight? What force is that? Weight is defined as the force of gravity. Yeah. Against a vertical wall and push it towards the wall with a force of 55 newtons. Ooh, this is a little different. So let's go ahead and draw an FBD for this. Be very careful. You are placing a block up against a wall. So think about gravity, but also think about the normal force and your force as well. You're pushing up against a wall. Think about your directions and forces. Well, here's FG, always, right? I'm pushing up against the wall. So if I have a block like this up against a wall, my force pushes this way. This is the force applied of 55 newtons. Now, if my surface is like this, the normal force is always perpendicular to the surface. So where should the normal force point? Well, the normal force is actually going to point outwards now because that is perpendicular to the surface. Yeah. Then there is friction here between the wall and the block. Now we need to think about this here because if I'm pushing this block up against the wall, the normal force is going to equal my applied force. Those should cancel out because if they don't cancel, what will happen is I will push the block through the wall. They have to cancel mathematically, logically. If they don't cancel, there's an acceleration up against the wall and the block is not going to go through the wall. Yeah. So the question says, does the block remain at rest? Well, if these are equal, if the block is to remain at rest, what that means is the force of friction pointing upwards would need to equal the force of gravity. So we need to see, does the block remain at rest? What this question is saying is, can we overcome static friction or not? So basically what we need to see is if Fg is going to be greater than the force of static friction. If Fg is greater than the force of static friction, the block is actually going to slip. Yeah. If not, that means you're pressing hard enough and the block will stay in place. Again, this is something you should understand. You should understand that in order to keep something pressed up against a wall, you have to apply a certain force to keep it there. If you like relax a little bit and then it goes shoof and it slides. So if we increase the normal force, we increase the friction between the block and the wall, and that can fight against the force of gravity for the object. So what I want you to do is I need you to find the force of gravity. Sorry, it's there. Sorry, don't need to find it, it's there. But we do need to compare it to the formula for static friction. Careful that you are doing the static friction. They give you two coefficients here. I'm sorry, this should be a little k. That's kinetic friction. We're using our static friction first. Again, if the question is, does the block remain at rest? You need to see if we can overcome static friction. So go ahead, plug in over here. Sorry, that's the normal force. See if it's bigger than 33. Well, I got 0.42. My normal force, hey, we determined that was going to be equal to what I pressed with, so 55. Let's go to calculator real quickly here. $23.1, let's see. 20. So is this a true statement? Is 33 greater than 23.1? Yes, what that means is gravity overcame static friction. So is the block going to move? Yes. Block is in motion. Now, if I do not want the block to move, again, if I don't want the block to slide down the wall, what should we do? What you're probably thinking to yourself is press harder. Mathematically, we should increase the normal force, because if I can increase the normal force, I can make that side of my equation bigger, and then that side of my equation would be bigger than gravity. But again, it really is pressing up against the wall harder. Now I'm going to go ahead and pause here only because this video is taking longer than I would like to. I'm probably going to go ahead and just finish this with you guys when I get back. But I wanted to get at least a bit more practice with the friction, especially if you already kind of plowed through the lab and you got it all done. We'll continue these last few slides when I get back.